For this next portion of the lecture, we're going to continue on, and now we're going to discuss some of these different types of stresses. For this particular slide here, we're going to be taking a look at axial loading and the normal stress here. So now one thing to note is that the resultant of the internal forces for an axial loaded member is going to be normal to the section cut perpendicular to the member axis here. So we can see if this is our section cut right here on this example right here, here's our load right here, which is going to be normal to that section right there. We can see we have this small area right here, our delta A, and this is located in an arbitrary cross-section point right here in the member. So now if we're looking at our formula and our definition for our normal stress right here, this is the force intensity on that section. And what we see here is we have our sigma is equal to the limit is our delta A. There's our small cross section, our delta A right there, approaches 0 of delta F, there's our delta F there, divided by our delta A again there, or our average stress here is equal to our load over our cross-sectional area. So this is our basic definition for normal stress right here. Now, something else to note here is that the normal stress at some particular point may not always be equal to the average stress, but the resultant of the stress distribution must satisfy the following relationship here. So our load, our P right here, is equal to our average stress times our area, which is equal to the integral of dF, which is equal to the integral of our sigma dA. Next, we're going to take a look at the difference between centric and eccentric loading. So a thing to note here, a uniform distribution of stress in a section is going to infer that the line of action for the resultant of the internal forces is going to pass through the centroid of the section. You can see there's our centroid right there. Now a uniform distribution of stress is only possible if the line of action of the concentrated loads P and P prime, there's our P load right here and our P prime load right there, passes through the centroid of the section. There again is our centroid of the section. You can see that this does pass right down through that centroid of that section right there, and this is going to be referred to centric loading. So this is our definition for centric loading, and we can see here in figure 1.12 we have a diagram illustrating that centric loading, again having those resultant forces passing through the centroid of the section. So now if we're talking about eccentric loading right here, take a look at our definition down here. A two-force member is eccentrically loaded, then the resultant of the stress distribution in the section must yield an axial force and a moment. So these stress distributions with the eccentrically loaded members cannot be uniform or symmetric. So we take a look at an example over here in figure 1.13. We have an example of an eccentric load right here. In A, you can see there's our load P, our P prime right there. Does not pass through the centroid at some distance away, which is going to create that moment right there. Or looking at just the top half right here, or I'm sorry, the section half of this right here in B, if we cut it right along that centroid location there, you can see there's the moment, there's the load right there. There's a distance right here off of this guy over there. So next we're going to take a look at shearing stress. So we can see we have forces P and P prime right here, P and P prime, and these are going to be applied transversely to the member AB. So here's our member AB right there. Now the corresponding internal forces acting in the plane of section C are going to be called our shearing forces. And now this resultant of the internal shear force distribution is going to be defined as shear of the section and is equal to the load P right there. Now how does this relate to our shear stress? Well, we have this definition down here that our average shear stress is going to be shown by this relationship here, that our average right here, average stress is equal to our load over our area right there. So there's our load again right there, and then we have our cross-section area A right here, and this is going to give us our shear stress definition. So the thing to note about shear stress is if we're at the member surface, this is going to be at 0. And then it's going to vary as it goes away from there and could be much larger than the actual average value that we're seeing here for our tau sub average right here for our average shear stress. So with that being said, we must also take into account that this shear stress distribution cannot be assumed to be uniform. So on this slide here, we're going to show a couple different examples of shearing stress. Let's take a look at single shear and double shear right here. So we can see an example on the left-hand side. This is a bolt subjected to single shear here. So you can see you have this member here and the force associated this way heading off to the right. We have our F prime force from this member over here, right here, and this puts this bolt right here in a single shear like that. Now, if we have a double shear, what we can see over here on the right-hand side, we have this bolt right here subjected to double shear. So what we can see here is you got these two members, C and D right there. But then you've also got A and B, and A and B, you're pulling on these guys here, pulling it. And now what we can see is down below each of these single and double shear examples, we have our diagram for what the bolt is like in shear. So if we take a look on the left over here for the single shear situation, we can see in point A, you have a diagram of the bolt in single shear. So you see this force is going one way. This force over here, F prime, is going the opposite way. So now we have the bolt right here. If we section this at EE, right there, you can see you have your force coming in here and your force F prime coming in here like that. Take a look at part B, and you have the section view at EE, or EE prime right there. And there you have your load coming in here and your shear right there of P right there. So there's your shear force P right there. Now, in order to go from there to get our shear stress, again, we recall that average tau sub average is equal to our P over A, so that's our load P right there. There's our cross-sectional area at that section right there for our A, where this P and this F are going to be equal to each other, so this is going to be equal to our F over A for our average shear stress for a single shear situation. Now, for the double shear, we come down here to our second diagram on figure 1.19. This is a diagram of the bolt and double shear right here. So there's two section views we're going to look at right here. So we're going to section it right there and right there as we come across it like that there. Or if we're dealing with bolt H and J right there, then we have those two spots right there. We're going to shear it right there. So then what we do is we take a look down here. You can see we have, okay, here's our bolt from H to J right there. We have our KK right there, section we come across right there. K and K prime right there with the surface of that there. And we have our L and L prime, so right there for our LL prime section right there. So we can see we have our F sub C coming in, F sub D coming in, and our F right here coming in right here. So here's our F corresponding to that there. Our F sub C and F sub D correspond to these members right here pulling out. So you have those three forces acting on the bolt from this double shear. So those are your shear forces right there. We then go over to B, take a look at our section view right here. We can see there's our shear force P right there, and our F force coming in like that. So what we have for an equation now, if we're talking about a double shear, our average stress, our tau average right here is equal to P over A, where our P is going to be that F force right there still, all over A. A is going to have two sections of cross-sectional area right here. So if you look, there's a top cross-sectional area and a bottom cross-sectional area. So that leaves us with this relationship right here. The tau average for a double shear is equal to F over 2A. Next thing we're going to take a look at is bearing stress in connections. So if we're talking about bolts, rivets, pins, these are going to create stresses on the points of contact, or what we're calling our bearing surfaces of the members that they connect. Now, the resultant of the force distribution on the surface is going to be equal and opposite to the force exerted on the pin. We can see that over here in figure 1.20, equal and opposite forces between the plate and bolt exerted over the bearing surfaces. You can see there's your bearing surface right there. There's your load P coming out here, whereas you have your forces coming in here on the actual bolt right there. Now, the bearing stress is going to be this corresponding average force intensity, and it's given by this definition down here. Sigma sub B, our stress here of the bearing, is referred to as our sigma B, and this is equal to P over A. Or if we take a look down here, and we're talking about this cross-sectional area right here, we can go down to this diagram here, figure 1.21 for the dimensions for calculating the bearing stress area here, and you can see the diameter of the pin is given here as D, the thickness of this plate here is T, so therefore the area here that we're going to be dealing with is P over T times this diameter D right there. So now how does this stress analysis we've been looking at here tie into our design work here? So we're taking a look at now at a similar problems that we've done before in the past for an example problem. In this case here, what we want to do is determine the stresses in the members and connections of the structure shown. So we haven't really talked about much of the connections with a problem like this here. So from our static analysis, we can come up with The following relationship here, we do all our free body diagrams, take a look at our summations of forces and moments. We know our distance over here, we know distance here, our external load right here. So we're able to go through our statics as we've seen in the previous example problem and calculate our F sub AB and determine it's in compression and our F sub BC and to determine that it is in tension. Now for our design consideration, we must consider the maximum normal stresses in both of the members, our AB and our BC right here. So this is right here being our BC member, this right here being our AB member, and also at the shearing stress, now that we've talked about our shearing stress a little bit here, and bearing stress at each pinned connection. So we can see we have a pinned connection here at a pinned connection here at B, and a pinned connection here at C. So each of those, we're going to have to take a look at our shearing stresses and our bearing stresses as well when we're designing this out. So we haven't really talked about the individual pins before when we went through this problem. We just talked about, okay, if we start introducing stress in here, we want to see what material we make it out of and what the diameter would need to be. And that's great, but we're going to take it a step further and make it even more realistic and say, okay, we've designed it now so that it's fine and that member, that diameter is fine, the material's fine there. But what about these pins? What about these pins here? Take a look at our stresses there, make sure we have the right diameters for the pins and the right materials for those as well. So now let's briefly take a look at rod and boom normal stresses. So we've already done the calculations before from statics and found that the tension in the rod has an axial force of 50 kilonewtons. We've also seen now at the rod center the average normal stress in the circular cross section here. We have a circular cross section A that we've calculated before to be 3.14 times 10 to the negative 6 meters squared is the sigma BC of 159 megapascals. So if this were a problem we're working on in the textbook, this may be information that they just give you in the problem statement, or it may be a longer involved problem where we went through and used statics to solve all of this first. So at the flattened rod end, so we can see we have a flattened rod end right there, the smallest cross-sectional area occurs. And that's what we're interested in here is our smallest cross-sectional area. And this is going to occur at the pin's center line. Now we can take a look up here at our diagrams to double check, make sure we understand everything that's going on. There's our 40 millimeters right here, going across right here of our pin, of our head of our member right there. We can see the thickness right here from the side profile is going to be 20 millimeters, and we can see our pin diameter is 25 millimeters right there. So our A right here is going to be this 20 millimeter, our thickness right there, times our 40 millimeter, this width right here, minus our diameter of the pin right hole in the center right there, which is 25 millimeters there. We do out that calculation and area becomes 300 times 10 to the negative 6 meters squared. So now we can see our sigma right here, and our subscripts are very important as we're doing these problems out. So we understand what we're calculating here. So our stress at BC, at the end of it right here, is going to be equal to our P over A, where our P is our load that we calculated right there, our actual force of 50 kilonewtons, so that's that right there, all divided by our A, which we've just calculated above here, so we can bring that down and plug it in. So our sigma BC at the end is equal to 167 megapascals. Now this is for the tension force right there. We could go back through, as we saw in the previous problem, do it for compression as well, where we had that 40 kilonewton load there. Go through the same type of calculations and calculate our average normal stress there, and we'll find that to be negative 26.7 megapascals. Another thing to consider here is the sections of minimum area at A and B rather than C are not under stress since the boom is in compression and therefore pushes on the pins. So next, this is going to lead us into the pin shearing stresses. So for all the pins, we're going to have the same diameter. We're going to have that 25 millimeter diameter for all pins at A, B, and C. So therefore, the cross-sectional area A, B, and C are all going to be the same. Remember, definition here for area for a circle here is pi r squared. So for each of these pins here, we're going to have pi r squared right there. Pull our pi out front. Our r is going to be our 25 millimeters over 2 because that's our diameter. So we divided our diameter by 2 to get our radius here. Square that term. What we end up for our cross-sectional area for all the pins at A, B, and C is 491 times 10 to the negative 6 meters squared. Now let's take a look at these individually. If we're talking about point C here, the force on the pin at point C is equal to the force exerted by the rod BC. So therefore, our shear stress here at the pin, so again, make sure we pay attention to our indices here, Tau for our shear stress, C for point C. This is A average right here. So this is going to be our load, and our load from BC we saw was 50 kilonewtons, or 50 times 10 to the negative 10 to the third newtons, divided by our cross-sectional area. And we just determined that our cross-sectional area at each pin is going to be the same, of 491 times 10 to the negative 6 meters squared. We do this out here, and our tau C, our shear stress at point C right here, is equal to 102 megapascals. Now this was a single shear right here, as we can see in the diagram, but when we go to the pin at A, this is going to be in double shear with a total force equal to the force exerted by the boom AB. So we can see down here, this is a double shear down here. So we take a look now here for our equation. So our tau average at A, again, pay attention to our indices here. Our shear stress at A average is going to be equal to our load over our cross-sectional area there. So we go through, plug in our load right here. So this is going to be divided now. Our load is going to be P because it's our both those loads right there. So we have 20 times 10 to the third newtons divided by that same cross-sectional area. The area of the pin does not change at all. So we end up with this relationship down here. So we end up with our shear stress at the pin at point A is equal to 40.7 megapascals. So continuing on with our pin shearing stresses, it may be of interest for us to determine the section with the largest shear force. So we can see over here in figure 1.25, we have a free body diagram for various sections at pin B. So we can see we've broken this down into a couple different sections right here. And with each of those, we have an associated force applied to it there based upon the shearing load there. So we have our 1/2 AB, which is 20 kilonewtons, 1/2 AB there. We have our 1/2 Q over here, 15 kilonewtons. We have this force BC of 50 kilonewtons right there. And over there we have that. So we have these 5 different forces there. So we can see we have our load here at E is just going to be P sub B is equal to 15 kilonewtons right there. And we have our P sub G at the center here, where we have the largest load, our P sub G of 25 kilonewtons right there. And this is all taken from our free body diagram and doing out our summation of forces moments in order to calculate these forces at individual sections within our pin there. So from that there, once we've determined our largest shear force right there, we then need to evaluate the corresponding average shearing stress. So we can do this with this relationship here. Our tau sub B average is equal to our P sub G, which is going to be our largest shearing force right there, divided by our A. We've already calculated our area, cross-sectional area there for the pin, and now we have our load P sub G for our largest shear force there. We plug that in, we find that our tau average at B is 50.9 megapascals. Next, we're going to move on and talk about the pin bearing stresses. So in order to determine the bearing stress at A, so we'll just start with A first. We can see this is in our diagram right here, figure 1.22. In the boom of AB, we have our dimensions given to us here as T is equal to 30 millimeters. So we can see this is our thickness right here of 30 millimeters right there, and our pin diameter of 25 millimeters. So there's our pin diameter right there of 25 millimeters. So our stress here, our sigma B right here, for our stress of the bearing is equal to our load over TB, and we've shown that before in earlier slides to come up with this relationship here. So we plug in our known values. Well, we have our load here of 40 kilonewtons. We have our thickness here, we just determined to be 30 millimeters, so that right there is from our 30 millimeters right there, and our diameter is 25 millimeters, we plug that in right there, plug this all in, and we can see that our stress at the bearing right there is 53.3 megapascals. Now, if we wanted to determine the bearing stress at A in the bracket, we have this thickness right here. We have 2 of this 25 millimeter thickness. So this 25 millimeter thickness there, this 25 millimeter thickness there, because this is our bracket that now we want to determine it in, rather than our member AB for the first part that we did there. So we also have that this, so this is equal to 2 times 25 or 50 millimeters. And we still have our D is not going to change there. Our diameter right here of our pin is still 25 millimeters. So we can plug it into that same general equation. Our sigma sum B now for our bracket is equal to P over TD, where P is still that 40 kilonewtons there, doesn't change there. What changes now is this thickness value here, because it's now 2 times 25, because there's 2 sections of the 25 millimeter thickness right there, times our diameter right here of 25 millimeters. We do this out and we find that our stress in the bearing for the bracket is 32 megapascals. So now let's take a look at stress in a two-force member right here. So one thing to note here is axial forces on a two-force member result in only normal stresses on a plane cut perpendicular to the member axis. So we can see this illustrated over here in figure 1.26. There we have a member right there. You can see the two forces P prime right there. And then we can see right here a perpendicular axis right there. You can see this cut right through there. Break it apart into sections right here. You can see the middle diagram here, and this is equal to, and now you can see our stresses acting perpendicular to that member axis. Now our transverse forces on bolts and pins result in only shear stresses on a plane perpendicular to the bolt or pin axis. So the same type of thing here if we're talking about our bolt and pins. So we come down here to figure 1.27. We can say the same thing here. We put this our two member force right there, P and P prime. We take a look at our section in the center here, and now you can see we can have our shear stress right there. Now that was to note that was just talking about the plane that we said was perpendicular to the member axis, but axial and transverse forces may produce both normal and shear stresses with respect to a plane other than the one cut perpendicular to the member axis. So that's going to be something important to consider as we're taking a look at this. Where are we cutting this axis for our plane right there? Is it perpendicular to it or is it not? So that leads to the question of, okay, if it's not perpendicular to it, what could it be? Well, one option is we can talk about this oblique plane here. So now if we talk about stress on an oblique plane, we have this diagram shown here in figure 1.28, and you can see this coming in. There's our oblique plane right there going through our member right there. So it passes through a section of the member forming an angle. So our angle here of some degree theta, you can see there's our theta right there with the normal plane. So that's an angle with respect to the normal plane. So from our equilibrium conditions that we've seen, the distributed forces and stresses on that plane must be equivalent to our force P. So what that means now is if we're not talking about something that's going to be perpendicular to it or in line with it, we're going to need to resolve these into terms of its components. So we're going to need to do a little bit of trig here. So resolve P down to the components of normal and tangential to that oblique section there. So we end up with the relationship shown here in these equations here when we do out our trig. Our F is equal to our P times the cosine of theta, and our V is equal to, our shear is equal to our P times the sine of theta. And we can see that over here in our diagram in point C there. There's our F, P, V, and our angle theta right there when we look at that broken down. So this leads us now that we have our average, normal, and shear stresses on the oblique plane are given by the following relationship down here. Break that down. Our sigma is equal to our F over our area theta right there. So we have to calculate that out there. So we calculate that out there. We can take our A not divided by our cosine of theta, and F is simply our P times the cosine of theta doing out our trig. So we end up with here, when we break that down, our sigma for this oblique plane is equal to P over A naught times the cosine squared of theta. Same with our shear when we break that down, rather than V being over our A theta, do out our trig in the center section here, and what we end up with is we have P over A naught times sine theta times the cosine of theta. So next I want to talk about maximum stresses. So we've seen from the previous slide, we have our normal and shearing stresses for an oblique plane given by the following relationship here. Our sigma is equal to P over A naught times the cosine squared of theta, and our tau is equal to P over A naught times sine theta cosine theta that we just showed on the previous slide. So now our maximum normal stress occurs when the reference plane is perpendicular to the member axis. So we have this relationship down here. Our sigma max occurs when P over A naught right there, and our tau prime is equal to 0. Now, our maximum shear stress occurs for a plane at 45 degrees with respect to the axis there. So our tau max is given by this relationship here of P over A naught times the sine of 45 times the cosine of 45, or we can rewrite this here as P over 2A naught, which is equal to our sigma prime right there. Now we can take a look over at our diagrams right here. So here's our axial loading. Here's our stresses for when theta is equal to 0. So this is our sigma max right here of P over A naught. So that corresponds to this right here. But now when we're at the 45 degrees, for stresses at theta equals 45 degrees, for our tau max, we can see now right here, this is our tau max right there. Here is our sigma prime right there, coming off perpendicular to that 45 degree plane right there. So this is the relationship here of P over 2A naught right there. And there's our tau max of P over 2A naught right there. And then we do the same thing for stresses at a negative 45 degrees down here. And we can see our tau max is given to us as P over 2A naught. And our sigma prime is equal to P over 2A naught right there. So let's talk about stress under a general loading. So we have some object over here with multiple loads on some general body shape that we can see here in figure 1.30. So a member subjected to these general combination of loads, we're going to cut this into two segments by a plane passing through Q. So we can see down here in figure 1.31, we can do that. We pass a plane through Q right there. So the distribution of internal stress components may be defined by the following. So we have this relationship that we see here for our sigma x. This is going to be equal to the limit as our delta A approaches 0. And see, here's our delta A right there of our delta fx over our delta A. There we go. There's our delta fx right there over our delta A. And our tau xy is going to be equal to the limit as delta A approaches 0 of our delta vyx. So we can come over here, there's our delta V right there, all over our delta A, and our tau xz is equal to the limit as delta A approaches 0 of our delta Vz in the x direction there. So indices are something that's important to pay attention to right here. We're dealing with our tau xy, we're dealing with our tau xz. How does it correspond to our indices for our V up here there? Now our resultant shear is our delta V, and our normal forces is our delta F right there. So paying attention to what we're using for variables and the indices and how they relate back to our problem and our diagrams is going to be important as we're solving these problems out. Now for equilibrium, an equal and opposite internal force and stress distribution must be exerted on the other segment of the member. So let's take a look at the state of stress. So we see here in figure 1.35, we have positive resultant forces on a small element. So we have up here in the diagram just a small element right there at point Q. So there's our point Q right there, resulting from a state of general stresses. So we can see we have all of these stresses here. We have our taus and our sigmas and our delta A's for each of those along the way. So what we do now is we go down to figure 1.36. What we have here is a free body diagram of the small element at Q. So this is Q here coming down, drawing out our free body diagram. Now this is viewed on a projected plane that's going to be perpendicular to our z prime axis right there. So we can see right there, this is our x prime, our y prime axis right there, and there right here in the dead center is our z prime right there. So we can see in this free body diagram, we have our sigma y, our tau yx, our tau xy, our sigma x, our sigma y, our tau xy, our sigma x over here, and our tau xy over here right there. This is a great way to view this in 2D on our free body diagram. Nothing to note is the resultant forces on the positive and negative z prime faces that we're not seeing here are not shown, and these act through the z prime axis, thus do not contribute to the moment about the axis. So continuing our discussion with the state of stress, these stress components are defined for the planes cut parallel to the x, y, and z axes. So for equilibrium, equal and opposite stresses are going to be exerted on the hidden planes. So the combination of forces generated by the stresses must satisfy the conditions for equilibrium that we see here. So we have our summation of forces and summation of moments. So summation of forces in the x direction must be equal to summation of forces in the y direction, which must be equal to the summation of forces in the z direction, which is 0 for equilibrium. Same with our moments. Summation of moments about x, summation of moments about y is equal to summation of moments about z, which is equal to 0. So if we consider the summation of moments about z-axis right there, this is equal to 0. We can go back to the free body diagram on the previous slide, and we can see, okay, force times perpendicular distance. What do we have that creates a moment about z? Well, we have this shear stress, delta A, our tau xya, times this A minus tau yx delta A times A right there. So certain things will cancel out our delta A, delta A. So we have now 0 is equal to tau xy minus tau yx, or tau xy is equal to tau yx. So similarly, we can do the same thing for the moments about y and the moments about x. And we end up with the following relationships here. Tau yz is equal to tau zy, and tau yz is equal to tau zy over here when we do that on both of those sides. So only 6 components of stress are required to define the complete state of stress. The last thing I want to cover in the lecture for today is our safety factors. So the factor of safety. So for considerations, when you're designing something out, safety factor is a huge, huge deal. So a lot of things are going to go into this when you're doing out your calculations. So a couple of these things to consider here, I've highlighted in this list. Uncertainty of material properties. You really need to take a look at your material properties. Is it adequate? Uncertainty of loadings, uncertainty in your analysis, the number of loading cycles, types of failure you may experience, maintenance requirements, and deterioration effects. So if you're going to maintain the system, the machine, those are things that are going to be needed to list it out when designing this project or this machine. Important of member integrity of the whole structure. So individual members of it, as how do they tie into the entire structure. Risk of life and property, and influence of machine function. So these are all just very basic intro ones for factor of safety. Again, this is going to tie into your ME 171 course as we go down the line and start doing more design projects. So structural members or machines must be designed such that the working stresses are less than the ultimate strength of the material. So that's where our factor of safety calculations come in. So Fs is equal to our factor of safety, which is equal to our ultimate stress divided by our allowable stress. So this is our definition and key equation as we're dealing with our factor of safety.